pick a direction, any direction at all. Up, down, left, doesn't matter. Now imagine traveling in that direction for 46.5 billion light years. You still wouldn't reach the edge of the universe. You'd reach the edge of what you're capable of seeing, which is a very different thing. And the difference between those two ideas is about to break your understanding of everything into pieces. We're taught to think of the universe as one single complete thing, all of it, everything that exists. But there's a wall built into the sky itself, an actual boundary, the same distance away in every direction you look, past which no telescope humans will ever build, no matter how powerful, will ever be able to see. Not because we haven't invented the right instrument yet, because it's physically, permanently impossible, built into the rules of light and time themselves. And here's the part that should genuinely unsettle you. That wall isn't the edge of the universe, it's the edge of our view of it. What's sitting past that wall, whether it's more galaxies exactly like our own, some entirely different kind of physics, or literally nothing at all, is one of the only questions in modern cosmology that may be permanently, structurally unanswerable. Not because we're not smart enough, but because the universe itself may have built the question to have no accessible answer. So what actually is this wall? Why does it exist at all? And what the best physicists on Earth currently think is sitting on the other side of it? Let's go find the edge.
To understand why there's a wall at all, you have to understand what observable universe actually means, because it's one of the most commonly misunderstood phrases in all of astronomy. It does not mean the universe as far as we've explored. We haven't explored it, any of it, not directly. Every single thing astronomers know about the universe beyond our own solar system comes from one source: light and other forms of radiation, arriving at our telescopes after traveling here for however long it took. That means every observation is automatically also a measurement of time. When you look at a galaxy 2 million light years away, you're not seeing what it looks like now. You're seeing light that left it 2 million years ago. You are quite literally looking into the past every single time you look up. So here's the natural next question. How far back can we possibly see? The universe is roughly 13.8 billion years old, so the absolute oldest light that could exist anywhere is light that has been traveling since almost the very beginning. And that's exactly where our wall comes from. Roughly 380,000 years after the universe began, something changed. Before that point, the universe was filled with a hot, dense plasma, a fog of charged particles so thick that light couldn't travel through it in a straight line for any meaningful distance, constantly scattering off free electrons the way headlights scatter uselessly inside actual fog. The universe, for its first 380,000 years, was completely physically opaque. Then, it cooled enough for electrons to combine with nuclei and form neutral atoms, a moment cosmologists call recombination. In the instant that happened, the fog lifted. Light, for the first time in the universe's history, was free to travel in a straight line. That first burst of freed light is still traveling, right now, in every direction. We call it the cosmic microwave background, and it is, by definition, the oldest light that can possibly exist, which means it marks the absolute outer boundary of anything we could ever hope to see. Not because there's nothing there, because there's no light older than that anywhere in the universe for us to receive. Here's the part that trips almost everyone up the first time they hear it. That boundary isn't 13.8 billion light years away. Even though the light has been traveling for 13.8 billion years, it's roughly 46.5 billion light years away. That sounds like it breaks the light speed limit, but it doesn't. The universe itself has been expanding the entire time that light was in transit. The galaxy that emitted that ancient light wasn't 46.5 billion light years away when it emitted it, but the space between here and there has been stretching for nearly 14 billion years since, carrying that source further and further away while its light was still crossing the gap. By the time the light finally reaches us, the place it came from has drifted much farther away than the distance the light itself traveled. That stretching is also why the observable universe is roughly 93 billion light years across, rather than the comparably modest 27.6 billion. Expansion, not speed, is doing the extra work. Before you can even ask what's beyond that wall, you have to sit with a harder question first. Why does that wall look so suspiciously uniform?
When astronomers first mapped the cosmic microwave background in detail, they found something that should not have been possible. The temperature of that ancient light is almost perfectly identical in every direction, uniform to better than 1 part in 100,000, whether you measure it on one side of the sky or the exact opposite side. On the surface, that might not sound strange, but think about what it actually requires. For 2 regions of space to reach the same temperature, they normally need to have been in contact, close enough for long enough for heat to flow between them and even out, the same way a hot cup of coffee eventually matches room temperature. But the 2 opposite edges of the observable cosmic microwave background are so far apart that in a universe expanding at the ordinary pace scientists originally assumed, light, the fastest possible way for anything to travel or exchange information, would never have had enough time since the Big Bang to travel from one side to the other. They should never have been in contact. They should never have had the chance to equalize their temperature. And yet they match almost perfectly. Physicists call this the horizon problem, and for decades it sat as one of cosmology's most stubborn contradictions. Something clearly connected those regions early on, but nothing should have been fast enough to do it. In 1980, physicist Alan Guth proposed a solution so strange it took years for the field to seriously accept it: cosmic inflation. The idea is that in an almost unimaginably brief fraction of a second after the Big Bang, somewhere around a trillionth of a trillionth of a trillionth of a second in, space itself expanded at an exponential, faster-than-light rate, not objects moving through space faster than light, which relativity forbids, but space itself stretching, which relativity actually allows. Before this brief burst of inflation, the theory suggests that eventual sky-spanning CMB was actually not far away at all. It was a small patch that light easily had time to connect every part of it, evening out the temperature completely. Then inflation seized that small evened-out patch and blew it up by a factor of at least 10 to the 26th power, a number so large it's easier to describe than to picture, stretching that small evened-out region into something now spanning the entire observable sky. Inflation also elegantly solved a second related puzzle, the flatness problem. Every precise measurement we've ever made says the geometry of space is flat, or so close to flat that we can't currently measure any difference. Parallel lines stay parallel. Triangles add up to exactly 180 degrees, the ordinary geometry you learned in school. That's a strange coincidence in an ordinary expanding universe, since almost any starting curvature should have become dramatically more obvious over billions of years, not less. But inflation, expanding a small region by such an enormous factor, would flatten out almost any initial curvature automatically. The same reason the surface of a giant balloon looks locally flat to an ant standing on it, even though the whole balloon is curved. One theory,
two of cosmology's biggest open contradictions solved at once. That's exactly why inflation, despite sounding like something like science fiction, is taken so seriously by working physicists today. Before we go further, if the idea of standing on the literal edge of what light has ever reached hasn't fully landed yet, we built an entire video specifically around just how vast even the observable portion is, zooming continuously from Earth all the way out to that 93 billion light-year boundary. It's linked right here, and honestly, this video picks up in the exact spot that one ends. But inflation, if it's correct, doesn't just explain our observable universe, it implies something enormous about everything past it.
Here's where inflation stops answering questions and starts creating new, much stranger ones. If a small patch of space could inflate by a factor of 10 to the 26th power in a fraction of a second, there's no obvious reason that process should have been unique to us, or perfectly uniform everywhere, or that it should have stopped cleanly and completely across all of existence at once. In the 1980s, physicists including Andrei Linde and Alexander Vilenkin worked out the logical extension of Guth's theory, now called eternal inflation. The math suggests that inflation, once started, may not actually stop everywhere at the same time. Instead, it could end in scattered regions, each one settling down into an ordinary, stable universe like our own, essentially a bubble that stopped inflating, while inflation continues eternally in the space between those bubbles, endlessly spawning more of them. If this is correct, our entire observable universe, everything we have ever measured, mapped, or photographed, would be just the inside of a single bubble, one among a theoretically infinite number of other bubble universes, each permanently physically cut off from every other one by space that is still inflating faster than light could ever cross it. To put the scale of that first inflationary burst in perspective, expanding by a factor of 10 to the 26th power is roughly equivalent to a single bacterium, too small to see without a microscope, suddenly ballooning to the size larger than the entire currently observable universe in less time than an electron can complete a single orbit. And under eternal inflation, that process is proposed to have happened, and to still be happening, in a genuinely uncountable number of separate regions. This is usually what people mean when they casually say multiverse, not parallel dimensions from science fiction, but a mathematically serious, if unconfirmed, extension of a theory that was originally built to solve two very real, very measured problems in cosmology. And here's an important, honest complication. Not everyone in physics is comfortable with where this leads. Paul Steinhardt, one of the original physicists who helped develop inflationary theory in the 1980s, later became one of its most prominent critics, specifically because eternal inflation, in his view, may predict literally any outcome somewhere across its infinite bubbles, which risks making the theory impossible to disprove. A theory that can explain any conceivable observation starts to raise an uncomfortable question. Is it still testable science, or has it drifted into something we can no longer verify by observation at all? That debate hasn't been resolved. Some of the most respected physicists alive today genuinely disagree about it. There's a second related mystery running underneath all of this. Is the universe actually infinite? The flatness we measure is consistent with an infinite universe, but it's equally consistent with a universe that's simply enormous, finite, but so vastly larger than our observable patch that any curvature would be too subtle for our instruments to detect, the same way the Earth looks flat if you can only measure a few kilometers of it at a time. Astronomers test this by measuring enormous cosmic triangles, using the known physical size of patterns in the cosmic microwave background as one side and their apparent size in our sky as the angle,
and checking whether the angles add up to exactly 180 degrees, the way they would on a flat sheet of paper, or something more or less than that, the way they would on the curved surface of a sphere or a saddle. Every measurement so far has come back flat within a very tight margin of error, but flat within our margin of error and flat period, forever, infinitely, are not the same claim. And with our current technology, infinite, and so large it might as well be infinite, produce nearly identical measurements from inside our one small observable bubble. We may never be able to tell the two apart. So, is there more universe beyond the wall? Almost certainly, according to the leading theory. Is it more of the same? Galaxies, stars, the same laws of physics, stretching out forever? Possibly. Could some of those hypothetical other regions formed in separate inflationary bubbles have settled into different fundamental constants, different physics entirely? Nobody currently has a way to check.
You might assume that whatever's beyond our observable horizon is simply waiting for better telescopes. It isn't. And this is the part that makes this genuinely different from most open questions in astronomy. Every other unsolved mystery in astronomy, black hole interiors, the nature of dark matter, what's happening inside Sagittarius A star, is, at least in principle, something better instruments might eventually help resolve. This one is structurally different. Light from beyond the observable universe hasn't just failed to reach us yet. Under standard cosmology, it can never reach us at any point in the future, no matter how long humanity survives or how advanced our instruments become, because the space in between is expanding in some regions faster than light can ever cross it. This isn't a limit of technology. It's built into the geometry of an expanding universe itself. And the situation is quietly getting worse in a way most people have never heard of. Because of dark energy, the mysterious force accelerating the universe's expansion, distant galaxies are gradually being carried away from us faster and faster. Right now, we can still see roughly 2 trillion galaxies, but billions of years from now, an enormous number of the galaxies visible tonight will have redshifted beyond any possible detection, permanently. Their light stretched into wavelengths no instrument could ever recover, their existence unprovable to anyone looking from Earth at that point. Trillions of years from now, according to current models, observers here would see nothing beyond our own local group of galaxies, no cosmic microwave background, no evidence of the Big Bang, no way to reconstruct any of the history we're able to measure right now. Future scientists, doing everything correctly, could look up and conclude the universe was small, static, and eternal, because the evidence proving otherwise will have physically, permanently vanished from view. We are, in a very real sense, living in an unusually privileged moment in cosmic history, a window of time when the evidence for our universe's origin is still visible at all. That window will not stay open forever. On the research side, this hasn't stopped physicists from testing inflation's other predictions as carefully as they can. Detailed maps of the cosmic microwave background, particularly its polarization patterns, are being searched for a specific signature, a faint swirling imprint called B-mode polarization, which primordial gravitational waves from the inflationary period may have stamped into that ancient light. Ground-based experiments like the BICEP array at the South Pole, along with planned space missions such as Lightbird, are built specifically to hunt for this signature with ever-increasing precision. Finding it wouldn't prove eternal inflation or the multiverse directly, but it would be strong supporting evidence for the inflationary period itself, the mechanism the entire idea depends on. It's a genuinely active, ongoing search, not a settled result waiting to be popularized, but a real open question current instruments are working on right now. There's a philosophical weight to all of this that's worth sitting with honestly, separate from the physics. We happen to exist during the roughly 100 trillion year window
out of an effectively endless cosmic future when the evidence for our universe's origin is still visible at all. That's not a comfortable thought, but it is, as far as anyone can tell, simply true, and it's part of why observational cosmology, unusually among the sciences, has an expiration date built into it. So the honest answer to what's beyond the observable universe is this: probably more universe according to our best current theory, but quite possibly a version of more that we are permanently barred from ever confirming directly by the same physics that makes the question worth asking in the first place.
So we end up somewhere strange. We've mapped in extraordinary detail a boundary that isn't the edge of reality, just the edge of what light has had time to show us. We've found strong evidence in the smooth uniformity of the oldest light in existence that something connected regions of space that should never have touched. And the leading explanation for that evidence quietly implies that our entire observable universe, every galaxy we've ever photographed, all 93 billion light-years of it, might be one bubble in something unmeasurably larger. We may be looking at the whole of existence, or we may be looking at a single room in a house we will never be able to leave, mapping its walls in exquisite detail while remaining permanently unable to open the door. Maybe future physics will find a clever, indirect way to test what's beyond that boundary, some subtle fingerprint left behind, the way the cosmic microwave background itself was once just a theoretical prediction before anyone actually detected it. Or maybe this is simply where science quietly runs out, and everything past this point stays exactly what it is right now, the most well-reasoned guess a species that can measure light 13.8 billion years old has ever been able to make about what it cannot see. If that thought lands somewhere between unsettling and genuinely exciting, that's the correct reaction, and it's exactly why this channel exists. Subscribe and turn on notifications so you don't miss the next deep dive. If you haven't already watched the video that leads directly into this one, the full zoom out from Earth to the edge of the observable universe, it's linked right there, and watching it first will make everything in this video click into place even harder. Here's the question for the comments. If you found out tomorrow with absolute certainty that everything beyond the observable universe was permanently unknowable forever, would that make you more curious, or would you rather have never known the wall was there at all? Let us know what you actually think. We read everything, and it shapes what we cover next. Thanks for watching. We'll see you in the next one.